Fluctuating. Most people think fasting lowers blood sugar, that skipping breakfast or extending the gap between meals should naturally make glucose levels drop. It sounds perfectly logical. After all, if you're not eating, where would the sugar come from? Yet, in reality, something surprising happens. 018. Many people notice that their blood glucose actually rises during fasting. It seems completely backwards, like your body is playing a trick on you. But this isn't a mistake or a sign that something's gone wrong. It's your body doing exactly what it was designed to do, maintaining energy balance in a state of food scarcity. 037. To understand why this happens, we have to look beyond what's on the plate and into the powerful hormonal systems that control blood sugar, especially the roles of insulin, cortisol, and the liver's remarkable ability to make glucose on demand. When you fast, your body begins to rely on stored energy rather than incoming calories from food. 056. The first source it turns to is glycogen, a stored form of glucose in the liver and muscles. This reserve provides a quick and easily accessible supply of energy to maintain normal blood sugar levels for several hours after your last meal. However, glycogen stores are limited and typically deplete within 2004 hours of fasting, depending on a person's activity level and metabolism. 118. When glycogen levels fall, the body must find an alternative way to keep blood glucose within a stable range, especially since certain organs like the brain and red blood cells depend almost entirely on glucose for fuel. At this point, the liver becomes a central player in maintaining glucose availability through a process called gluconeogenesis. 138. This term literally means making new glucose. Rather than drawing from stored carbohydrates, the liver begins to synthesize glucose from non-carbohydrate sources, primarily amino acids from muscle tissue, lactate from anaerobic metabolism, and glycerol from a breakdown of fat. This process ensures that even during prolonged fasting, the bloodstream contains enough glucose to meet the body's essential needs. 204. Gluconeogenesis is not a random or uncontrolled event. It's a tightly regulated hormonal process. When insulin levels fall during fasting, a signal is sent to the liver that energy intake has stopped. At the same time, counter-regulatory hormones such as glucagon, cortisol, and adrenaline increase. 224. These hormones act like switches that turn on the machinery of glucose production. Glucagon released from the pancreas tells the liver to start converting amino acids and other substrates into glucose. Cortisol secreted by the adrenal glands enhances this effect by increasing the availability of those substrates. Adrenaline or epinephrine further stimulates the breakdown of stored energy, ensuring a continuous supply of raw materials for glucose synthesis. 251. The liver's ability to produce glucose is an evolutionary adaptation that kept our ancestors alive when food was scarce. In a fasting state, the body must prioritize energy for the brain and vital organs, even if that means breaking down other tissues to fuel them. This process might sound destructive, but in the short term, it's a protective mechanism designed to sustain life. 313. It also demonstrates that blood glucose is not solely dependent on food intake. The body has intricate internal systems to maintain energy balance even in the absence of eating. Interestingly, this process explains why some individuals observe an increase in blood sugar levels during fasting periods. The liver, responding to hormonal cues, releases glucose into the bloodstream as part of its normal function. 338. This can make it appear as though fasting is raising blood sugar when in fact it's simply maintaining the energy supply. The body's goal is not to achieve the lowest possible glucose level, but to keep it within a functional range. The rise in glucose during fasting therefore reflects the effectiveness of these internal regulatory mechanisms, not a failure of metabolism or evidence of problem with fasting itself. 402. During fasting, the body experiences a shift in its hormonal environment that fundamentally changes how energy is managed and how blood sugar is regulated. The most significant of these hormonal changes involve a rise in cortisol, often referred to as a stress hormone. Although cortisol has a reputation for being harmful when chronically elevated in the context of fasting, it plays an essential and adaptive role. 426. Its primary function during fasting is to ensure that adequate glucose remains available for critical organs, particularly the brain, which depends heavily on a steady supply of glucose. This rise in cortisol along with other counter-regulatory hormones such as glucagon and adrenaline explains why blood sugar can increase rather than decrease during periods without food. 446. When food intake stops, insulin levels naturally fall. Insulin's main job is to help store energy by moving glucose from the blood into cells. When insulin decreases, the body interprets this as a signal that energy intake has halted and it needs to switch from storing energy to releasing it. 506. In response, cortisol begins to rise. Cortisol stimulates the liver to produce glucose through gluconeogenesis, a process that converts non-carbohydrate sources like amino acids, lactate, and glycerol into glucose. This newly produced glucose then enters the bloodstream to maintain normal levels, ensuring the brain and other glucose-dependent tissues continue functioning efficiently. 530. Cortisol also enhances the effect of glucagon, another hormone released from the pancreas during fasting. Glucagon acts as a direct counterpart to insulin. While insulin stores energy, glucagon releases it. Cortisol amplifies glucagon's message to the liver, making glucose production even more effective. 548. Meanwhile, adrenaline, the body's fast-acting stress hormone, contributes by breaking down glycogen stores and increasing free fatty acids in the blood. These fatty acids serve as an alternative energy source for muscles and other tissues, allowing glucose to be spared for organs that require it most. 608. The rise in cortisol is part of a broader pattern known as a counter-regulatory response, a system designed to maintain glucose levels when food intake drops. This mechanism ensures survival during times of scarcity by mobilizing internal resources. The liver, under the influence of cortisol and its hormonal partners, essentially becomes a glucose factory responding precisely to the body's needs. 630. While this process can cause measurable increases in fasting glucose levels, it is an expected and healthy physiological response rather than dysfunction. It's also important to understand that cortisol's influence on blood sugar varies depending on timing and individual context. During early fasting or short-term intermittent fasting, cortisol levels may show only mild ONS. 651. However, during prolonged fasting or in people under significant stress, cortisol levels can rise more sharply, leading to a more noticeable increase in blood glucose. This response is not just a reaction to the absence of food, but part of a coordinated effort to protect the body's most vital systems. In this way, the increase in cortisol and other counter-regulatory hormones during fasting is a carefully orchestrated adaptation, allowing humans to function effectively even when meals are delayed or skipped. The body prioritizes energy. 720. Distribution through hormonal control, ensuring that glucose remains available precisely where and when it is needed most. When blood glucose rises during fasting, it often triggers internal confusion, especially among people who expect fasting to always reduce sugar levels. However, this rise is not an error in the body's design or a malfunction of metabolism. 740. It is a natural and intelligent adaptive response that has been shaped by thousands of years of human evolution. The human body is built for survival, and fasting is one of the oldest physiological challenges it faces. In such situations, the body must keep critical organs supplied with energy even when no food is coming in. 759. This balancing act is accomplished through a series of coordinated hormonal and metabolic changes designed to maintain blood glucose within a narrow functional range rather than allowing it to drop dangerously low. During fasting, insulin levels fall and counter-regulatory hormones such as glucagon, cortisol, and adrenaline rise. 819. These hormones signal the liver to begin releasing glucose into the bloodstream. This release can come from stored glycogen or be produced through gluconeogenesis, where the liver creates new glucose from amino acids, lactate, or glycerol. This process keeps blood sugar levels stable, ensuring that vital tissues, especially the brain, have a continuous energy supply. 839. The slight elevation of glucose during fasting reflects this normal response as the body shifts from depending on dietary carbohydrates to relying on internal energy production systems. From an evolutionary standpoint, this mechanism made perfect sense. Early humans often went hours or even days without eating. 859. If blood glucose simply fell to zero during fasting, survival would be impossible. The body therefore evolved to anticipate fasting periods and activate its internal glucose maintenance systems to keep energy flowing. This is not a sign of dysfunction, but a clear example of the body's ability to adapt and self-regulate under changing conditions. 919. The temporary rise in blood glucose seen during fasting represents the successful execution of this system, not a breakdown of it. In people with insulin resistance or metabolic disorders, this adaptive rise can appear more pronounced. The liver may release more glucose than necessary, and the body cells may not respond as effectively to insulin signals. 941. Even so, the underlying process is the same. It is the body's attempt to preserve energy balance and protect critical functions. The key difference lies in how efficiently the system operates. For a healthy person, glucose production during fasting is tightly regulated and limited to what the body needs. For someone with metabolic imbalance, the same mechanism can overshoot, leading to higher blood sugar readings. 1003. But even then, the process itself is not inherently harmful. It is the context and background metabolic state that determine its impact. This natural rise in glucose during fasting also helps explain why fasting blood sugar measurements can sometimes seem inconsistent. A person might find their morning glucose higher after a long fast even if they haven't eaten anything. 1022. This phenomenon, often referred to as a dawn effect, reflects the same adaptive principle, the body ensuring enough glucose is available to start the day's activities. Such responses highlight the body's remarkable ability to maintain stability through constant internal adjustments, keeping energy available even when external fuel sources are temporarily absent.